Hi everybody, and welcome back to our overview of the history of plant classification and nomenclature. In this lecture, we're going to pick up the story in the second half of the 18th century. After the publication of Linnaeus's work in 1759 and the acceptance in Europe of his binomial system for naming plants and animals, the next important advance in plant classification was made by the French botanist Antoine Laurent de Jussieu. Remember, Linnaeus had classified plants into genera based on the number of each of their floral structures. Jussieu took all of the existing genera and further classified them into families. He defined a family as a group of plants with a definable set of similar physical characteristics. These characteristics weren't just limited to floral structures, though. His work was published in 1789, the year that the French Revolution began, and he used his system later to display plants in the Jardin des Plantes that you can see here in the photo, which is a botanical garden in Paris where he was the director. Jussieu also classified families into a higher rank called class, and his work formed the basis for much of the plant classification ranks or taxa that are used today. By the beginning of the 19th century, several more taxonomic groupings had been created, which resulted in the hierarchical ranking that you can see in the diagram here. Organisms were first classified into a kingdom, either plant or animal at that time, and then based on physical characteristics, they were further classified into a phylum, which for plants is also known as a division, and then into a class, order, family, genus, and species. This hierarchical system worked really well for classifying all of the plants from across the world that were being brought back to Europe. A series of questions could be asked at each taxonomic rank that enabled botanists to identify plants as well as classify them. The questions they asked might have followed something like the diagram on the next slide. The levels in this family tree-like diagram roughly represent the hierarchical ranks shown on the previous slide, from kingdom down to species. Note that this diagram includes algae in the plant kingdom, but modern classification systems place algae in a separate kingdom, the Protista. You can see that examination of the physical characteristics of a plant enabled taxonomists to place it in the appropriate hierarchical ranks based on whether the plant was vascular or non-vascular, whether it produced from spores or from seeds, whether it produced an ovary or no ovary, and whether or not it was a monocot or a dicot. Below this, a plant could be classified into a family based on a defined set of physical characteristics, then into a genus, and then into a species. The taxonomic rank of family was particularly useful in identifying plants, as many families have a distinct set of physical characteristics that distinguishes them from other families. Family characteristics remain important today in plant identification, and you'll be learning the characteristics of several plant families in the labs. The concept of family isn't important just from plant identification and classification points of view, though. It's also really important in plant production, where having an understanding of which families plants are in can be important when you're considering weed and pest management and crop rotation strategies. Having an understanding of families is also important in arboriculture from a pest and disease risk management point of view. In urban forests, there's what's called the 10-20-30 rule for tree diversity in cities. This rule suggests an urban tree population should include no more than 10% of any one species, 20% from any one genus, and 30% from any one family. With greater world exploration, more and more plants were being named, and inevitably names were duplicated. Remember, unlike common names, the botanical name is supposed to be a unique identifier of a plant in order to avoid confusion. So the duplication of botanical names was a problem. Remember, this was the mid-1800s. Communication by telegraph between the US and England only became functional in 1866, and the first phone wasn't invented until 1876. So snail mail transported by sea and land was really the only way to communicate if you wanted to check on the name of a plant with fellow botanists either in the same country or across the world. An additional problem was that there were no internationally accepted rules for naming plants. So, in 1867, a meeting of European and North American botanists was convened in Paris. Their goal was to compile an internationally accepted set of rules for naming and classifying plants. At that Paris meeting, Linnaeus's system of binomial nomenclature was accepted as the starting point for the naming of plants. Rules governing the naming of plants and the syntax of the different taxonomic ranks were agreed upon, and we'll look at those in another lecture. The rules established at that conference in 1867 were laid down in a document called the International Code of Botanical Nomenclature. The code has since been reviewed and revised several times, and the current version is the 17th, which was accepted in 2018. The rules are administered by the International Association for Plant Taxonomy, and you can access all of the rules on this organization's website. You should also note that the publication containing the rules had a name change in 2011 to the more precise name of the International Code of Nomenclature for Algae, Fungi, and Plants. The hierarchical system of plant classification that I described earlier can be described as artificial from a plant evolution point of view, meaning it doesn't reflect any relationships between plants. The system really was just a glorified filing and naming system that allowed scientists to communicate about plants more easily and more accurately. The opposite of an artificial system is a natural one, which does reflect evolutionary relationships. So why was the system artificial? Well, you have to remember that the dominant religion was Christianity in Europe, Russia, and as a result of colonialization, North America. Christianity believed that all organisms were created by God. Therefore, evolution could not possibly exist. It wasn't until 1859 that theories of evolution by natural selection were made public in Charles Darwin's book On the Origin of Species. Darwin agonized over the publication of his theory because he realized it would be seen as heretical in many circles, and he was really concerned that he'd be ostracized by his peers. His theory of evolution and natural selection did become accepted by the science community, and taxonomists realized that the most scientifically valid system of naming species would be a natural one which reflects evolutionary relationships. Consequently, at the end of the 19th century, plant taxonomists adopted the goal of developing a natural system of classification in which closely related organisms are classified together, and where plant names are assigned on the basis of phylogenetic or evolutionary relationships, which initially were inferred by studying plant physical characteristics together with fossil evidence. Since the beginning of the 20th century, what used to be known as the science of taxonomy, which is the process of classifying organisms, has given way to the science of systematics. Systematics is the study of living organisms and the relationships between them. So this is quite a long lecture. There are probably about 7 more minutes to go, so this is a good place to take a break if you want to. Just hit the pause or the stop button and go stretch your legs. Let's take a look at which characteristics plant systematists use to classify plants. Linnaeus's classification of plants into different genera was based only on the reproductive structures. He counted the number of stamens and pistils. Other botanists realized that his system was flawed and that, as John Ray had argued in the late 1600s, all plant parts should be considered. Remember that in the early days of plant taxonomy, the characteristics that could be considered for identification and classification were restricted by the magnification limitations of microscopes and the quality of their lenses at that time. Up until the 20th century, plant physical characteristics such as the vascular system, leaf arrangement, leaf venation, hairs, armaments, which are prickles and thorns, the number of cotyledons, plus of course reproductive structures were considered when deciding what rank or taxon to classify plants in. Fossils, too, have also been used since the late 19th century. Since 1965, the introduction of the scanning electron microscope has enabled taxonomists to look very closely at the surface structure of plant parts such as pollen, hairs, stomata, leaf cuticle and waxes, and to use these features in classification. Depending on the quality of a scanning electron microscope, magnification can be up to 2 million times. Improvements in light microscopy have also enabled taxonomists to look more closely at internal structures, such as cell structure and their organelles, and take these features into consideration too. And advances in the understanding of physiological processes, metabolic pathways, and the chemical structure of compounds mean that these too are also now used in plant classification. The discovery of the role of chromosomes and the structure of DNA in 1952 has resulted in molecular data also now being used to classify plants. The analysis of molecular data combined with fossil evidence has enabled scientists to propose new theories about the evolutionary history of plants. This history is depicted diagrammatically as a phylogeny, and it's represented schematically in a diagram called a phylogram. A phylogram is a branching diagram which depicts evolutionary relationships between species or groups of organisms based on similarities or differences in their physical, chemical, and genetic characteristics. The length of the branches on the diagram can represent the relative amounts of time involved, although this isn't always the case. The goal of phylogeny is to trace each organism or group of organisms back to a common ancestor. The organisms with that common ancestor can then be classified together in a group or clade. In the diagram here, you can see a simple phylogram which illustrates the evolutionary history of land plants. The long diagonal line represents time from around 450 to 500 million years ago, when plants first started to colonize the land, to the current era up in the top right-hand corner. Each of the branches off this line represents the evolution of different groups of plants, and you'll look at this diagram again in the next module. The intersection point of branches, for example, here, here, and here, is where it's thought there was a common ancestor. For example, at this point right here, it's believed that there was a common ancestor from which all of the gymnosperms and all of the angiosperms, the flowering plants, evolved. And as I mentioned a couple of seconds ago, we'll come back and take a closer look at this in the next module. It's important to remember that our knowledge of plant evolution is incomplete and that phylogenies include many hypotheses. Plant systematists don't always agree with each other on these hypotheses, so classification systems are under constant debate and change. As technology and our understanding of plant science and evolutionary relationships improve, it's inevitable we realize that some plants were misclassified in the past. Consequently, these plants are reclassified by plant systematists, and sometimes this involves a name change. This can be really frustrating for those of us trying to learn plant names. It's really frustrating too for the horticultural industry, as nurseries have to make new labels and marketing materials, and websites have to be updated. Sometimes it can take several years for a new botanical name to gain widespread acceptance and usage in the horticultural industry and among consumers. And books, of course, only get updated with the new names if a new edition is published. These name changes are something you need to be aware of as you're looking up plant information for this class or for your jobs. An example of a relatively recent name change resulting from new molecular data is the South African succulent Coumera plicatilis, the fan aloe, which you can see in the picture on the right. This plant was reclassified in 2013 from Aloe plicatilis to the different genus of Coumera. You can see this plant in Cabrillo's Southern Hemisphere garden, on the succulent mound in the upper garden, and in several local landscapes. Many people in nurseries still refer to it as Aloe plicatilis, and will probably do so for many more years, especially as the name aloe is in the common name. So let's finish this video lecture by summarizing what's been covered. After the acceptance in Europe of Linnaeus's binomial system of nomenclature, plants were named and classified into a hierarchical system of ranks depending on their physical characteristics. From the late 19th century onwards, after acceptance of Darwin's theory of evolution, the goal of classification changed from an artificial system based just on physical similarities to a natural system which reflects evolutionary relationships. Improved understanding of plants' molecular structure, physiological pathways, and internal structure are also used to classify plants now. And new developments in this can result in plants being reclassified and renamed. Rules governing the classification and naming of plants are laid down in the Botanical Code of Nomenclature for algae, fungi, and plants. That's the end of this video lecture. Go take yourself a well-earned break now, or if you've got some stamina left, head back to Canvas and continue with this module.